You know, every single time you tap your phone, click a mouse, or stream a show, you're conducting an invisible orchestra. An orchestra that doesn't play music, but runs on a silent, secret language made entirely of numbers. So let's peel back the curtain, shall we? We live our lives through these beautiful, user-friendly interfaces. But if you could strip all that away, layer by layer, what would you find at the very bottom? What is the actual native language that the processor at the heart of the machine really speaks?
And that's exactly where we're headed. We're going to bypass all the friendly software we're used to and travel right down to the bare metal. We're going to look at the raw, fundamental instructions that make everything else we do even possible.
So first things first, what do we even call this secret language?
Well, it's called machine code. And look, this isn't a language for you and me. It's not meant to be read by humans. It's designed for silicon. It is the most direct, the most primitive way to tell a computer what to do. Just a raw stream of numbers that the CPU understands instantly. And this right here, this shows you the huge gap perfectly. On the left, you've got a simple command we can all read. Print hello. Easy enough. But on the right, that's what the machine actually sees. B83412. So the big question is, how on earth do we bridge that gap? For our journey today, our guide isn't some dusty old manual. Nope, it's this fantastic little artifact, a real-world lab report from a student who was tasked with getting their hands dirty and speaking directly to a microprocessor. All right, so let's meet the person behind this report and figure out what exactly they were trying to accomplish.
So this report comes to us from a student named M.D. Raju for his microprocessor and interfacing lab, and his assignment was about as old school as it gets. Manually enter a program into this piece of hardware called a trainer kit. No compiler, no fancy software, just a person and a machine.
And his goals, written right here in the report, were crystal clear. First, he had to figure out how to translate some basic instructions into the machine's numerical language. Second, he had to physically punch that code in, one number at a time. And third, the moment of truth. Run the program and see if it actually did what it was supposed to do. A simple challenge, but a really fundamental one.
So let's get into the nitty-gritty. How did this translation actually happen byte by byte?
Think of this table as his Rosetta Stone for the processor. On the left, you've got assembly language, which is kind of like a middle ground between our language and the machine's. The first command, MOV AX1234H, just means, hey, take the number 1234 and put it into a super fast little storage spot called register AX. The machine code for that specific instruction is B83412. The next line copies that value over to another register, and HLT just means stop, you're done.
So, when you put it all together, those three simple instructions boil down to this, a sequence of just 6 numbers. That's it. That's the entire program that M.D. Raju had to communicate to the processor.
And the process was completely manual. He had to power up the board and then, using a keypad, literally punch in each of those 6 bytes. B8, click, 34, click, 12, click, and so on. You get the idea. No copy-paste to save you here.
Okay, so after all that careful translation and all that painstaking button pushing, did it actually work? This is where we find out.
And boom, there's the payoff. The whole point was to load 1, 2, 3, 4 into register AX, then copy it to BX. And this table, right from his observations, shows it all. The expected value and the observed value, they are a perfect match. A flawless execution. It worked.
And you can almost hear the satisfaction in his own write-up. He confirms that the program ran exactly as planned, verifying the data transfer was correct. Mission accomplished.
So, okay, a cool little experiment on some pretty old hardware. But why should we care about this today? Why does understanding this low-level process still matter at all?
Because, and this is the key takeaway, no matter how advanced and slick our software gets, this is still what's happening at the very core. Every beautiful app, every complex algorithm, it all eventually gets broken down layer after layer, until it's just a simple list of numbers, just like the one in this lab report. For really demanding stuff like high-end video games or the systems in our cars, developers still need this level of control to squeeze out every last drop of performance.
And the student's own conclusion really drives the point home. This whole exercise wasn't just about moving numbers from one place to another. It was about fundamentally grasping the process of how a human idea becomes a machine's action. This is the bedrock that all of modern computing is built on.
And that kind of leaves us with this wild thought for the future. We've spent 100 years building all these incredible layers of complexity so we don't have to speak in numbers. But as artificial intelligence gets more and more powerful, creating its own logic, we might be entering a world where the most complex language isn't ours, but the machine's. What does that even look like? Definitely something to chew on.